Hi everyone, my name is Andy McMahon. I'm Machine Learning Engineering Lead at NatWest Group, based in Edinburgh in Scotland. And I'm really excited to be here today as part of the RSS conference to talk to you about what I like to call the 4P's of successful data science. In particular, this is a talk about how to make projects successful in industrial data science, which I've got a few years experience of working in and leading analytics and machine learning engineering teams. So yeah, I just want to get stuck right into it. So what are the 4P's that I'm talking about? So in a nutshell, I think these are the most important things really for any project to be successful, but also for any data science team or initiative or even strategy to be successful. And the four components that I'm referring to are really the people that you employ, hire, and work with, the processes that you use to really take those people and have them work towards a common goal, the product you aim to build at the end, and the patterns that you work against to do so. And I think these are all pretty much equally important, but they all have particular aspects that we really want to focus in on and understand in order to make that data science project a success. So in the next 20 minutes, I'm going to try and just give you a flavour of some of my thoughts and experiences across all of these areas. So we'll start with people. So people is such an important topic in data science, and it's really one of the ones that's potentially the easiest to overlook since we're so excited about the technology, the algorithms, the data. And you may have seen a diagram like this floating around in different venues, different forums, which is basically a Venn diagram trying to say what the ideal data scientist looks like. And really, I don't like this diagram that much, but what I do like about it is when you kind of change the focus of it. Instead of thinking about one person or one topic of data science, you really start thinking about how to make a blended team that covers all of these different aspects. So I think for your data science team to be a success, you'll have to cover all of these points: computer science, business domain expertise, maths and statistics knowledge. But really, you should do that as part of the wider team. No one person should really fit that bill. So as part of that, you'll start thinking about things like on the computer science side, what sort of programming languages do you want to use? So I've worked in situations and in companies where we use Python, we could use Scala, even places have used Java. It doesn't really matter. What matters is just that it's really understood what you need to make it successful in the environment that you're in, and that you build a team really around that knowledge. You then have to start thinking about how those teams of people really stick together. So how are you going to organize the people that you have to make that blended team a success? So here I've just shown a rough diagram that could be how one project or one department's organized, with leads and senior engineers and scientists feeding down into other engineers and scientists. But really you have to think about how are they going to work together to take this blended team approach and make it successful. You have to think about the technology and infrastructure you're going to use more widely. We'll come on to a bit of that later in some of the other P's. But you have to think, how does all this translate and come together and really work as one unit? And then you have to try and hire people, not just for their technical skills and for their breadth across some of these domains, but how successfully are they going to help people integrate their knowledge between the different domains, these different blobs in this Venn diagram, and that's through communication. So really, are you hiring and educating and coaching your people to become the best communicators that they can be, so they can bridge all these gaps and make sure that we hit that sweet spot in the middle as part of that blended team. So I think that's really important in that people P. And then one of the key ways that you bring all these people together is by having a coherent vision for what data science and data strategy is in your area, in your domain. So I think that vision that you articulate to your people should always be focused. It should be really clear what you're going after. Don't try and say things like you're going to solve AGI in the next few years, but really be focused in on how you are going to make data bring value to your initiatives or to your research project. You really need to be relevant. So in industrial data science, we're always thinking about how are we relevant to the business that we're part of? How do we really focus and help support that business domain column that's so important for translating what's often quite a theoretical exercise into real value. And then finally, how do we make the vision exciting? So if you're going to have people come with you in the journey, join your team, work with you to build products, then the vision that you articulate really has to be exciting. So I don't think there's any hard and fast rules here, but I do think these are three of the things that I've found have been most important to make data science and machine learning initiatives not just nice ideas on paper, nice theoretical exercises, but initiatives that save companies and customers millions of dollars of value every year. And a big part of that as well, that I'll just finish on with this section, is one important aspect of people in this space is your customer. So at the end of the day, who is your customer? Are they an internal customer? Are they an external customer? Who are you eventually feeding your results, your knowledge, your solution to? So in data science, this could be anything from a fully kind of automated backend API that's feeding some other customer-facing application, or it could be an internal stakeholder here, like this PhD supervisor, who just needs to know what data you have and what it means. But really understanding that customer is such an important part of making your data science story a successful one. The next P I'm going to come on to is a bit more technical. So this is around patterns, and in particular software and architecture patterns. So we should always bear in mind how machine learning and data science solutions really boil down to their key components. They can be very complex, but at the end of the day, they're just about taking data, often feeding them into models, whether they be sort of statistical models or kind of more machine learning based models. But at the end of the day, it's really about that cycle between data and models and helping us make decisions. So the options here, A, B, and C, how do we know that C is the right one, and with what kind of confidence can we give them? So if we just always boil down to the fact that whatever pattern we're going to work towards should really have these components at the end, so data, models, and then decisions, then we won't go far wrong. But under the hood, as I say before, that can become quite complicated. So what's important is not that these things are never going to be complicated, but understanding that although they may be complicated, you can design patterns and leverage architectures that already exist, but then reuse them. So reuse, repeat, recycle, essentially. So here I've got two kind of screenshots taken from some of the microservice and machine learning lens architectures that Google Cloud and AWS suggest to use. And there's absolutely nothing wrong with you basing solutions totally entirely on these architectures. In fact, they encourage you to do it so that you use their solutions, but you can use this with any type of hardware infrastructure backing it up. The key thing is that once you've settled on a pattern that you think is going to be useful, you reuse it and just adapt it for your particular use cases. And this reduces kind of the cognitive overhead whenever you start a new project. What do you have to design? What do you have to really come up with from scratch? If you have these patterns to hand and you can leverage them again and again, that just saves you so much time, so much energy, so much money, and means you can move quicker towards value. And again, meaning that you take those people that we spoke about in the first P, and you can really make sure that they're put to work against a really strong skeleton of the project. And then you have a vision towards which you want to execute successfully again and again. And the final point I'll just finish on that is remember that whenever you're trying to succeed in industrial data science, you're not actually just doing science, you're also trying to think more towards this engineering piece, this ML engineering world. And how the solution might look for these different camps, if you like, might be slightly different. And it's important that we can kind of translate smoothly from one to the other. So bear in mind when you're doing your scientific statistical experiments, you're always trying to think what's the end engineering product, and these patterns that you're using should really help articulate that vision as well. The third P that we're going to talk about is one that I think is extraordinarily important and again can be easily overlooked, and this is process. So by this I could mean really any of the processes that you use in executing your projects, but in particular I'm thinking here about the development process, particular to data science and machine learning projects. So it's important to recognize, first of all, that as we'll know, machine learning, data science is not traditional programming. There's very rarely a straight recipe for how you solve a certain thing. There's a lot of good ideas and a lot of good examples that already exist, but really most things are a bit more research oriented. So I like to always think that each machine learning or data science project has an R and a D component. And it's just really around some projects have a larger R, larger research element. Some have a larger D, larger development component. But at the end of the day, it's not just a traditional programming function. You have to think about it differently. And process is a huge part of that. So often when I've worked in teams or led teams, we've worked to a pattern of development that really doesn't stray too much from this one. There's usually 3, 4, maybe 5 stages, doesn't really matter, but at the end of the day, they cover these key points. So you'll often have a discovery phase where you really understand the business, the problem, understand what you're trying to get to, and really trying to define that in some sort of statistical or numerical measure that you can then build against and work towards. Next stage of the process will be playing around and understanding how that could work, at least at some high level in practice. So doing some experimentation and say it's Python, the Python ecosystem in your Jupyter notebooks, maybe writing some queries, getting some dummy data sets, playing around with some community editions of tools like say Databricks, but really starting to understand how what you've discovered in the previous part of the process starts translating towards a solution. You can then start thinking about how you develop that into the final end product. So how do you bring software development practices into this data science project, the machine learning engineering piece that I've mentioned before? Start thinking about testing. How do you version control your models? What's your baseline performance going to be like? How are you going to actually work? Are you working in sprints and Scrum and Agile? Or are you doing something else? And the final piece of this process is really the deployment phase. So you have to understand how you're going to package up the end solution. What's your deployment strategy? How often are you going to update? What infrastructure are you going to use? Is your documentation in a good place? How are you going to monitor performance? Are you going to work to CI/CD, continuous integration, continuous deployment, DevOps type practices? And these are all important aspects that really won't necessarily touch a data science project if they're not in an industrial setting, but they're so important when you're doing industrial data science and making it a success. If you don't think about this deployment piece as part of the process, then you won't have a solution that actually serves and creates value on a day-to-day basis often. And then just finishing up on that point, the transition from engineering to that end monitoring piece of the process is so important that I actually went and wrote a book that has a lot of stuff to say about this. So just 2 of the images I've got in the book, I'm talking about what I call the transition from ML engineering to ML ops. So here on the left, I've got this idea of the model factory, I like to call it, where your training system builds a model that gets stored and then feeds into your prediction system. And then you have things like drift detection to understand if your model in operation needs retraining or is actually suffering some other kind of degradation of performance that needs investigated. And then your processes should also incorporate how you're actually going to store your models. So here I call it the train persist process, where you have your pipelines that do the ingestion of the data, the feature engineering, training of the model, but then you'll need some sort of model store. And these are quite important aspects that feed into your process. Quite technical points, some of these, what's under these boxes or circles. But at the end of the day, it's all about process. How do these things link together into a cycle that allows you to generate value again and again? And obviously, for more information, I would recommend you look at my book on that. And then finally, the final point I want to cover off, the final P, is really the product we're trying to build. So often, as I've already alluded to, we're not just trying to build a one-off analysis. We could be doing that, and that's absolutely fine and valuable. But often we're trying to do something that interfaces with other software or other solutions, or even becomes its own standalone product, but it's something that's consumed and used by users. And that's quite important, because it's not a simple thing to do that. And in fact, there was a paper that some of you might have heard of a while ago by Google that was called Hidden Technical Debt in Machine Learning Systems. And the idea here was that whenever you build a software solution with machine learning in it, there's so many other pieces other than the ML code. So here you can see lots of boxes doing various different things: serving infrastructure, configuring the solution, extracting features, verifying the data. And the actual piece that's ML code is actually just this little bit in the middle, this tiny little black box in the center. So a lot of our industrial data science effort is actually about building and working out how to integrate with all of the other boxes around this ML code piece. And that's where the ML engineering idea comes in, and where all of these P's that I've mentioned come together to make sure that we've covered all the bases through our people. We're bringing them together in a standard architecture pattern, that we're working to a good process so that we can execute the build of all of these different components, and then we can build something that works together. And another important set of points for products is that products obviously work. So you're used to your iPhone or other solution that is machine learning really working day in, day out. So we have to test. That's so important for this product-oriented data mindset. Products get delivered, so we don't need to spend time reinventing the wheel. We're doing very sort of naive analyses. We should leverage what already exists. We should really build on that and just try and push towards the solution that we should really be going after that delivers value. And then understand that products come in a variety of shapes. So there's not necessarily one size fits all. We can work to standardized patterns, of course, but we should be flexible in that, and we should build solutions that can then be changed and extended later. So some patterns like microservice architectures are particularly good for this, where we can add extra components and extra functionality as and when the time comes. And then just bear in mind that this has been done a lot of times before. So I've just put up some logos and pictures here of well-known products that you'll all know will have active machine learning teams and machine learning and data science teams working on them. And they all integrate quite successfully in these products that we all know, love, and use. So it has been done before. Although you might not be working on the shiny new thing like a voice assistant, you might be working on more a kind of standard backend process that feeds into a database. You should still think as if you're working to the same high quality of product, and you're still trying to deliver something that's not just necessarily a machine learning model, not just necessarily a piece of analysis. Again, it could be that, but often I think what really delivers value is the integration with other systems into this very strong product. And so with that, I'd like to just say thank you so much for your time. Thank you for listening. And if you want to get in touch with me, here's some places where you can find me. I'm on Twitter at electricouija. I'm on GitHub. I'm on LinkedIn. I have a blog, electricouija.com. And as I already mentioned, my book is actually out in October this year, Machine Learning Engineering with Python. So hopefully you can check that out. And hopefully we have some time for questions. So thank you so much.